So what we will talk about, so basically we will consider this MG is a compact boundaryless, and it's C infinity Riemannian manifold with negative sectional curvature and dimension D. Okay, so if we talk about curvature, this is C2. So most cases you can think about C infinity matrices. So since we will use this notation, so I just put this curvature tensor here, the notion, later for calculation. So you will have this curvature tensor is the difference, this one, then minus. And we also use this sectional curvature notion as capital K of this UV is this one. Okay, so this is the notation we will use. So in many cases, actually, we will consider things in the lift of this MG. So we will go to the universal cover. So this M will equals to computer, the quotient space. This gamma is the fundamental group of this M. So let me give a basic example. That's the example we all know, say the two-dimensional hyperbolic space. This equals to, you will have Z is greater than 0 and Z minus. Okay, so you will have the metric tensor. Yes, square, then plus dy square, then minus d square. You have bracket. So it's the same as the disk model, concrete disk model. And here you have the d equals to x y, and you will have this z equals to this one. Okay, so this metric tensor is with this one, 4. Okay, there's 4 here. So, and it's the same as if you talk about this half-plane model. Y greater than this one. Then with the metric tensor given by this one, this dx squared, then plus dy squared, then divided by y squared. Okay. So we all know these three examples actually are the same, because you will have the So you will have the disk here, And it's the same as you think about the up half plane. And here you have the map from here. Here is +1 and here is -1. Then the map is, you cannot, you have this map, then it's isometric. Okay, so this is the basic example we have. It's of constant curvature -1. Okay, so no problem. So there are facts. The first fact is from Poincare and their book. Correct. Is for this two-dimensional hyperbolic space, there exist closed quotients by isometries. Okay, this is the first fact, and the second fact comes from the uniformization. Uniformization theorem, which says, is that too small or is that okay? Maybe it's too basic, so you don't need to see it. Okay. So any closed surface of genus greater than 1 will admit of constant curvature, negative constant curvature -1. So in many cases, you will see, for instance, a typical example is that you will always see this picture. You will say this is our mg, and then the universal cover of this one is just the Poincare disk, and the lift of this, you will have a fundamental domain, right? Like this, okay? So this is the basic example. Then the question is, do we have other examples? These are the of a negative curvature -1. Of course, you can just change this one into R, yeah, properly, then you will get constant curvature negative for R, right? So if there are other examples, so actually you have many other examples. The first class is if you consider the symmetric space. Symmetric space of negative curvature. So you have a classification of this one. I just put it here. Okay. It's analogous to the two-dimensional hyperbolic space case. This is N. You can go to Rm. In Rm, this is You have a classification of this, and all these spaces will have closed quotients. Okay, so these are examples. So since we will use this notion of symmetric space, we can mention the definition of this one. Okay, so what does that mean? If you have a manifold, okay, then for each point locally, you can have this exponential map, right? So you are given a geodesic, and then if t is very small, then you will have this gamma t and gamma minus t always exist. You have a point x here, and then locally in each direction you have a unique geodesic here, and then you consider the map from this gamma t goes to gamma minus t. Oh, so sorry. Yeah, yeah. So you consider this refraction. If we call it symmetric, if this map is well defined for every, and also this map is isometric. This is symmetric. Okay. If this can be defined globally, then actually symmetric spaces of negative curvature has to be non-compact. This is symmetric. But we also have another notion called locally symmetric. Means this map is defined locally as isometric map. Okay. This is locally. Locally symmetric means this is locally isometric. So the first classes of negative curved, the space we are interested in is these symmetric spaces. It can be considered as a little more complicated examples than the constant curvature case, right? So this is the first class. So another class is if you consider C2 perturbations of these matrices, and then you still have negative curvature, right? Because you have the curvature tensor there, and you can consider C2 perturbations of the above examples. Right? And actually, you can continue. I will say there are many other examples. Or at least candidates of IMG with negative curvature. So I won't view the complete list of these because I don't want to spend several minutes to write down the list. Another point is that you don't need to finish this list to find all the possible examples and candidates. By candidates, say, for example, I mean, if you have a hyperbolic group which is torsion-free, it's still don't know if you can find the MG with fundamental group as this one, and also negative curvature, okay? So there are many examples and candidates. You don't need to finish this list to join our game, because our game is like this. It's not our game, actually many people's game is we want to recognizing these symmetric spaces of negative curvature through these global properties. Okay. locally, actually, when we consider MG is locally symmetric spaces. Did I mention this? Okay. So locally symmetric, there's one characterization is the covariant derivative of this curvature tensor is 0. So it's a little more general than the constant curvature case. Okay. So we want to recognizing these locally symmetric spaces with negative curvature. Using global quantities, global quantities, okay, or properties. Maybe, yeah, or properties. Okay. So do we have examples or successful examples? One example is like this, an example. You already see this notion in Peter's lectures. If you pay attention, is the volume entropy. Okay, so what is that? You're given a mg, then you go to the universal cover of this one, and then you will consider this Vg, the volume entropy, is defined as the exponential rate of the growth of the volume. What does that mean? This is R goes to infinity, then you consider 1 over R of the logarithm of the volume of a ball centered at any point in this universal cover. I put m tutor here, then of radius R. Okay? So this is the volume entropy. So there's a famous theorem here called BCG theorem. It's Basu, Courtois, and Gallot in 1905 of this. So the setting is like this. You will let this mg, you have a mg naught, which is closed and locally symmetric. With negative sectional curvature. And you have another space, mg. Another metric means with the assumption that you will have the same volume for this m. Volume of in G of this m equals to the volume of G naught of m. So okay, with this assumption, actually you always have Vg, the volume entropy of m in metric G is always bigger or equal to the volume entropy at G naught. Okay, and you will have equality only if, if it's okay, let me put this. You will have equality only if this mg is isometric to mg naught. Can you see this part? Okay, mg naught. So that means if locally symmetric negative curved space has some kind of very strong rigidity. This is they will have the smallest volume. And if your volume entropy, volume entropy, and if you have another metric with the same volume of the whole space, and this volume entropy has to be bigger or equals to this one. And if it's equal, then this is isometric, okay, these two metrics. But they proved it for when the dimension of M is bigger than 2. So I want to put a remark here is actually this theorem also holds in the dimension 2 case. This is by Katok in 1982. So, okay, so. Oh, it's not the same. I'm sorry. Okay, it's not the same. Sorry. Dimension 2, I mean, in dimension 2, this is you will have the equality only if you have constant curvature. Thanks. Okay. So then we ask if there are other possibilities. Say that again. Both are what?
Both are localism. So I'll get the quality.
About most rigidity.
He's asking about most rigidity.
Oh, most rigidity. This is, yeah. This will imply that, right? Yeah, I think so. So, okay. So then, our question is if you have other possibilities. Question? Do you have other quantities? Okay. So in these 4 lectures, actually we will study the possibilities using dynamic quantities. Actually it's entropy thing, and we will begin with dynamic entropy, actually lots of entropies. And this part actually is related with the statistical related, let me see. Statistical properties. When we say a dynamic means related with geodesic flow. This is one typical example. Okay. This is on the unit tangent bundle. We will use this notation Sm as the unit tangent bundle. Okay, this is a dynamical point of view. And when you consider measures, you can also consider measures related to other motions. So what kind of other motions you will consider is you can consider the Fourier diffusions corresponding to the foliations of this on this SM. So another point of view is stochastic entropy. Also, this is a class which is related to foliated diffusions of SM. Okay. But then finally, we will show actually this stochastic thing is related to the deterministic thing. So what we will do, we will use the dynamic point of view to consider the diffusions. So that means we will consider this kind of relative dynamic entropy part, which is related to the geodetic, to the stochastic arising from these diffusion things. Okay. So this explains that the title of this series talks is Entropies for negative curved manifold. Okay, so this is a joint talk. With Francois Riddhipratim, by definition. Okay. So what we will do, actually we will spend maybe two lectures or 2+1/2 on this part. Because when we talk about these diffusion things, it will rely on our consideration of these foliations, and these foliations, we have several natural foliations which will arise from the geodesic flow. Okay, so we will spend 2+1/2 maybe lectures on this part, and then we will move to this stochastic entropy part, and these last two parts, we will spend 1+1.5 times maybe to give you the view how to relate these two parts. Okay. Actually, if you consider them from the dynamic point of view, the stochastic case is very similar to the deterministic case. But you have some new things. Okay. So let me begin with the things for geodesic flow. So the first part, actually, is on geodesic flow, and we will try to understand this flow using the Jacobian field. And we will have Horus spheres, which is related to the foliations we will discuss in the lectures. Okay? So what is that? We can draw a picture We always have this picture in mind. And what is geodesic flow? It's in the unit tangent bundle. So actually, if you have this V belongs to the unit tangent bundle, then actually you will have, because we're in the negative curvature, starts with the initial velocity of this with this V, right? Okay, so you have this geodesic. So T is considered no, actually T should, because in this case, so you will have a geodesic plus to n, such that so the initial velocity is this V. Okay, so what is the geodesic flow? Of course, we know this, but we need to introduce notions for this. We will use the notion of IT. You will map this V goes to the velocity at time t. So it's gamma V dot t. So this is the mapping, t time mapping of this geodesic flow. So for this flow, you have a vector field which generates this flow. So this is called the geodesic spray. We always use this notion. So use x bar V. This is in the tangent space. This is the vector field. Generating is phi t. Okay, so So with this flow, the first thing we want to understand is the tangent map of this flow, t time map. So we try to understand geodesic flow begins with the description of the tangent map, phi t at V. Okay, so how you describe this? I can draw a picture locally. So here is your V. You have the geodesic here. And then you consider a curve of V, Vs, with this V naught, another parameter, okay, right? S in parameter S, with this V naught equals to this V, right? Say, for example, your Vs is like this, okay? Then you have the geodesic. Locally is like this, right? When you consider the tangent map, you consider the tangent map of this phi t. So phi t, if you have a vector, initial vector, then your orbit is the geodesic, and you have your parallel transportation of this vector along the geodesic, right? So, okay. So if you vary your initial vector with another parameter, this S goes to Vs, okay, and consider this S goes to Vs. This is C1, and with this V naught equals to V, and it's differential in S at S equals to 0 equals to W. This belongs to the tangent space of this TV Sm, right? Okay. So then you consider time t map, and the base point, the derivative of this base point in the direction of s, in this, you have an n of that is called Jt, is the Jacobian field. You see what is this? If you consider this actually Jacobian field is the tangent of the variation of the geodesics, right? You start from Vs, then you go to time t. These orbits are all geodesics. So this is the tangent of the variation of this one parameter of geodesics, is Jt. So that means S goes to phi t Vs, the base point, of this one has tangent Jt at s equals to 0. And this Jt is a Jacobian field. This Jt will satisfy what? Actually, it will satisfy the Jacobi equation. This we will use from time to time, so we'll give the proof. So this is a proposition. The covariant derivative in this geodesic direction, gamma dot. This is gamma dot at t, right? Of this Jt, then plus, this is a curvature tensor of Jt, and this is gamma t dot, this equals to 0. Okay? So proof, you just use the definition of, so that means simply, this is by definition using the covariant derivative. It's covariant derivative in this way of t, then minus, exchange this, then minus the bracket. Have a look at this one. The first part is 0 because it's geodesic flow. This is parallel transported along the geodesics, right? So this is 0. And then this is also 0 because this is the bracket of this partial s and partial t, right? So this part also disappear, and you use this. You can exchange. You use this bracket is 0, then you can exchange this, and so you will go to this part. Okay, so this is the only left term is equals to minus okay, so this is the proof of this. And what we will use of this Jacobian field, you see there are several facts about this Jacobian field. several facts. The first one is about this, if you have J0 equals to 0, actually this will correspond to the vertical vector in the tangent, in this tangent space. So let me put it here. This will correspond a vertical vector omega in TVSM, right? If you have a not equals to 0, that means here this curve, actually you only change the directions. So this Jacobian field, this part, this J not equals to 0, actually at the initial point, this will correspond to the vertical vector, okay? And then you have the differential of this one equals to 0. Let me see. This current derivative at least is to 0, actually will correspond to a horizontal vector. Okay, so that means you can identify a Jacobian field. This J naught, J prime, it means the derivative in the V direction. This guy, you can identify this with decomposition. In the horizontal and vertical decomposition. Right? So this is the first part for this JT. And the conclusion is that when you consider the tangent map, if you are given with an initial variation of this V, with tangent omega equals to this vector. So if you have a vector, initial vector, then you consider the tangent map of this one. So what is that? Actually, you can show this. The tangent map will map this tangent vector to what? To JT and JT. So what does it mean? If you know the initial vector, the horizontal part is J naught, and the vertical part is, you give the notation of J naught prime. If you have a variation of your initial vectors in this way, then actually what is the tangent map at time t will bring your vector to the Jacobian field generated by these variations. You have your JT, and the vertical part is just the derivative of this JT in the t direction. Right? We can give a proof of this fact because we will use this observation from time to time. So we just get familiar with this. Okay, so we use the picture there. So what is the tangent map of the act on this vector? Actually is the horizontal part. The horizontal part will be the derivative of this gamma. You start with Vs, initial Vs, and your derivative at, no derivative. This is the horizontal. So this is the base point at t of this one, and then you will have the derivative s direction at s equals to 0, right? So then the other part is also in this way. Actually, it's gamma dot, right? Because you know phi t where it goes to this. Okay, so this is gamma not. Okay, so this is this one, and then actually this is just by definition, this is the Jacobian field at t, jt, and this you can exchange the derivative of s and t, then you get what? At this is just jt prime, right? You can exchange the order of differential. So the differential in s is just jt, then you take the differential in t, put prime here. So, okay, this is basic. And there's another fact which you can see is that if we assume this mg is negative curved, the space is negative curvature. Then a useful fact is that if you consider the map of T goes to, if you have a Jacobian field and you consider the norm of this one, you consider the map of T goes to JT square, the norm of this. So actually this map is what? Convex function. This is how you see this. I put square here, so the computation will be easier. Actually, you have similar results if you consider just the norm of this one. So again, we can give a proof of this one. Simple. So it's J square. This one is J, the inner product of this one, right? So, okay. So this equals to 2 times J prime, J. We take the first derivative. And then take another derivative. So this is what? This is 2. This is J double prime, and this is J, then plus 2 J prime, J prime. Right? Okay? Problem. And of course, this is positive. And how about this one? You have the Jacobian equation of this. You satisfy this, and you put it here. So the derivative in t twice is this one, so it's minus r. This is derivative of this is jt, right? Gamma at t. And here you have jt. Okay? So this is yes, then plus 2 J prime. So you see, if this is a negative curved, actually this term without minus should be less than some negative thing. So then this with minus is bigger than, right? Bigger than 0, so this is convex. This is a convex function. And what's the consequence of that is if you consider the exponential map, this S on MG on the no, not on MG, on the tangent space is a diffuse from Tx M. You have a point on M. You consider the map, exponential map. Actually, this guy is a diffuse from this one actually to what? We can consider this as M tutor. Because with the convexity, there's no conjugate point, right? So you can go to, oh, okay, sorry, I should not raise this. Okay, maybe I, these are useful facts. And now, we can give more notations of geodesic flow. We have many notations, but most of them already appear in the morning session, so it should be fast. So one thing is you add a boundary to this tutor. We go to the universal cover and tutor. So by boundary here, we mean the geometric boundary. And this is the collection of equivalent class of geodesics. By equivalent, we mean if you have another geodesic, half geodesic, which belongs to this, means the two geodesics remain bounded in bounded distance. Okay? So this is the geometric boundary. And then you see, if we go to the universal cover, actually if we consider the unit tangent bundle at the point x, any point x here, you consider the unit tangent bundle of SM, this with the notation of SM tutor at S. Actually, then because you have no conjugate point, so it's one-to-one map from, you give one direction, you will correspond to a point seeing the boundary and vice versa. So you have this map sending V to the equivalent class of gamma.
Lower bound section curve.
Negative curve.
Just section curve is negative.
Yeah.
Okay, but is this still the correct notion then? I mean, if there is a lower bound on the sectional curvature, then is being
G, MG, universal cover.
okay.
This is the universal cover of MG, so you don't have this problem. This is one-to-one. Okay, so that means we can identify the unit tangent bundle. This is the universal cover, okay? We always have this map. We always have this model in mind. This is negative curve. So M tutor, SM tutor can be identified with M tutor times the geometric boundary, right? Because each one can be identified with the geometric boundary. So the unit tangent bundle of the universal cover space can be identified with M tutor times the geometric boundary, okay? So we have this. And then one dynamic notion is about this weak stable manifold for the geodesic flow. Weak stable manifold. Okay, so that means if you are given any V, SM tutor, we can say, because we have this identification, so it's X Z, which belongs to SM tutor. Then the stable manifold at this point V is denoted by W tutor S. S means stable, okay? S, V, which is the collection of the initial vector such that the geodesics are asymptotically to C. So you have omega, which belongs to SM tutor, such that the supremum of t greater than 0 of your phi t applied to omega and phi t applied to V, this distance is bounded. Okay, so this is the weak stable manifold. You see this one actually can be identified with what? With M tutor times C. Because this V where it goes to C, and where in the negative curvature case, actually for each point you will have a unique, you start from here, any point here, you will have a unique direction, so that unique geodesic connecting this point Y and C, right? So actually the stable, weak stable manifold at V actually can be identified with M tutor times the point C. The collection of all these vectors, right? With a base point and with the direction pointing at. So this is the weak stable manifold. And now you see that this gamma acts, this fundamental group gamma actually acts continuously. I mean, I have to say, because this morning already see that you can add metric to this boundary, Gromov metric. Then with this metric, actually you can extend the action of the fundamental group to the boundary, okay? So then actually now the fundamental group actually acts continuously and discretely on the M tutor times the boundary, the product of these two. So you see one corollary is that the unit tangent bundle downstairs can be identified with what? With the quotient of the diagonal action of this gamma. Gamma is the fundamental group, okay? So this picture will always help because many times you will go upstairs to see things more clearly, and then actually you will apply ergodic theories downstairs, because here you are in the complex case. SM, and so this stable, weak stable manifold, also the downstairs object, I gave the same notation as V here. If you have a V here, you can lift it to the universal cover. And this weak stable manifold at V downstairs can be identified with M tutor times C, and also the quotient space, right? Okay, this is the stable manifold. And we already have the first foliation of S and tutor. You see upstairs, each stable, weak stable manifold can be identified with n tutor times C. So as this C varies, actually you will have a foliation of S and tutor. So this foliation will descend to a foliation downstairs of Sm. Where's Sm? Sm is here. So this foliation will be called the stable foliation. Okay? This is the class of foliation. It's the stable foliation. This is nothing this way. Yeah. As this C varies. Okay. So here we have. And another foliation is called strong stable foliation. But before we introduce this, we introduce the Boltzmann function. You also already see this Boltzmann function, which is like this. You have Bx C. Given x and c, you define the function at y to be this. Z goes to c, the difference of this dy. Z minus d x. Okay? So if you look at the picture here, so that means you have y here your x. The Boltzmann function, the value at y is you have some point z here. So the difference of this distance minus this one, and then that this z goes to infinity, goes to c. The difference of this one. So you see the one observation is that the gradient of this one is minus the geodesic spring. Right? This is minus x in this direction. X. Right, is minus in the opposite to the direction. Okay, and then yeah. X here you have a point x here. And you have c here. Yeah, x tutor cosine. And here you have the gradient, and then you take the gradient at y equals to x. So this is x size, maybe. And this is the Boltzmann function. Okay. So then what is the level set of this Boltzmann function? Is just the Horus field. The Horus field. I should say this is also with this notion as bx c y c. Okay, we are on this foliation on this stable manifold. So the level set y c prepare such that bx c y c equals to 0, this is the strong, stable manifold of the geodesic flow on the unit tangent bundle of M2. Okay, so this means strong stable here. We put W tutor SS here, XC is the collection of initial vectors of geodesics, and such that the distance as t goes to infinity of this gamma y c the distance of this one and the geodesic starting from xc at time t, the distance of this one will goes to 0. So this is the strong stable manifold. The picture is the Horace field. You can see this as the limit of what you have the V here, and you have the geodesic. Here's a C. So if you have a ball at each time at Z along this geodesic, then you have a ball centered at Z with the distance of dxz. Then you let this Z goes to infinity. Actually, this Horace field is the limit of these balls. Okay?
I think after you answered the third question. So X was a vector field on SM.
X bar.
Yes.
X C is, oh, okay. We are 48. So what's your question? Here is X bar, right?
Yeah, X bar was a vector field on the SM, on the unit bundle.
Yeah.
Yeah.
So here we have bar, X bar. Oh.
And what is X with no bar?
No. Here's bar, right? Oh. Right? Is that correct? Here is what? Y c. Is X bar, right?
Yeah.
If you define this. Yeah, here you have X bar. X bar is the geodesic spray. Okay? So this is the strong stable manifold. And again, it will descend to downstairs, you will have the strong stable manifold at V. V belongs to Sm. So this foliation locally, you will have this the 4 points of this one are the Horace field, right? Okay. So this is the strong stable manifold. So you will have another foliation. And now we will use notions like this. If you have divergence along this lift, along these leaves, S means along the weak stable foliations, the leaves of this one, and then you have the gradient from this one, and then you will have the Laplacian of this one, means the the divergence of gradient. This one. These are along WS or WS tutor with the metric you inherited from this G tutor. Okay? So then, the quantity, one quantity we will always consider is the Laplacian of this Boltzmann function. The Laplacian of this one. So actually it will equals to the minus of divergence of in this S direction of X. So this is this guy is a gamma invariant. Function on SM tutor. So you can also bring it to downstairs. So one observation from the flow point of view is that we'll have this result, which says it defines this quantity actually where equals to minus the derivative of the logarithm of the determinant of the tangent map of this geodesic flow in the strong stable direction. You restrict yourself to this direction and consider the derivative at time 0. Okay? Can you see this result immediately? From the point of view of vector field, if you have a vector field, or if you have a flow generated by a vector field, so actually you consider the tangent map, the determinant of that one, you consider its derivative in t, it should be e to the power of a divergence phi, right? So here it's the same. So this one is minus of this logarithm of this one is minus divergence. Okay, so this quantity. So what's the important, so maybe I have 5 minutes, okay? So why we're interested in this quantity? Because it's a geometric term, we will explain later. Actually, you can already see it, this is the mean curvature of the Horus sphere of this, this is the B, okay? So there's theorem. Which says B is constant if and only if this Mg is locally symmetric. So the proof, again, I won't give the proof because it's a deep result. Actually, I will give the reference here. So the reference is from library. 92, they have a paper, and then you need to pass library, also 92, then plus the BCG theorem we mentioned earlier, the rigidity result we mentioned earlier, for high dimensional case. So actually for dimension 2 case, you can see this immediately. So the dimension 2 case actually is simpler. Because in this case, the Jacobian equation, you also have the Riccati equation version, okay? So then you see this B satisfying what X in the geodesic direction is minus B, then plus minus B squared, then plus what? Plus the sectional curvature, this is 0. This is x-size, I put this as x-size. This is Riccati equation. So dimension 2 immediately you see, if this is constant, this is 0, so this sectional curvature is constant. So constant curvature, okay? So you see we introduced so many notations. So what do you need to remember? Actually, if I let you choose, maybe you don't know. If you let me choose, I choose this B. We will mention this B in the following lectures. And also, it's helpful to have this basic example in your mind. So you can try to see all these notions that I mentioned using this pancreatic model or this M tutor equals to the 2 and K equals to minus 1. So you will have the stable Jacobian field. Here's your X. Orthogonal, if your initial variations are orthogonal to your geodesic Jacobian field. In this case, actually is equals to e to the minus t orthogonal. So you will have the exponential decay, and decay rate is just minus 1. Yeah. Okay, and you have your BV. Is from the flow point of view, it's the tangent. This is E minus T, so it's 1. The mean curvature of this Horus field is BV. And you have your F. In this case, if you define Fx as e to the power minus the Boltzmann function, you have a reference point, x0, and you consider the Boltzmann function at S, and you consider this function. Actually, we'll find out this F is harmonic. We'll satisfy this. Finds this equation, it's a harmonic, and you can see this Fx as this Sx goes to c, actually will go to infinity, and if you let this x goes to other point in the boundary which differs from this c, it will go to 0. So this F, you will met this F next week. This is the Poisson. Okay, so this is F. And these are the only things you need to have in mind is this basic example. You will have the stable foliation, the strong stable foliation, and you have the Jacobian field, and you have this mean curvature of this Horus field, this B. And next lecture, we will start from this B to give you more things which is related to entropy and also related to the characterization of locally symmetric spaces. So I stop here.
single correction, C1 plus epsilon, something like this. Because for the definition of the Laplacian, what? Because
the Laplacian is along this,
no, but
along the,
why is it along?
along this strong stable.
Along the strong stable manifold.
Yeah.
Okay. It's okay.
Yeah.
No, but no, along the strong stable manifold, the function is constant. No.
Which one?
No, you take the Laplacian as a Guzman function.
Yeah.
But it's not along the strong stable manifold because.
This is Laplacian is the usual Laplacian.
Yes, but why is the function?
This is a holder. It's holder in Cassie, I think.
Oh, sorry.
It's holder in Cassie.
Function is C2 plus epsilon.
No, it's Cassie. It's holder in Cassie. It's smooth in X.
Yes, but the dependence in Y. Why is it C2 in Y? I just asking what the meaning of the Laplacian is, because the function is not very regular.
Not very regular in Cassie.
Why? As soon as you leave this point of but I don't remember the regularity, so maybe regular enough, but I know that this is the key point, that as soon as you leave
No, the regularity in Y is sufficient to have this definition. But in Cassie, it's not. Well, we can discuss. Yeah.
The foliation is not very regular.
Not very regular. So for the stable foliation, it's holder in Cassie. See.
That's the point.
That's why it's folder.
Yes, but
Well, we can discuss later.